Hello everyone, welcome back to the lecture series on magnetism in condensed matter physics. In the previous video, we have seen the origin of polyparamagnetism, which arises when the conduction electrons are weakly interacting and delocalized it to form the Fermi gas, and the magnetic response originates in the interaction of spins with the magnetic field, resulting in Zeeman splitting in the presence of magnetic field. And we have seen that the temperature independent susceptibility in this case is given by mu naught mu v square times density of state at Fermi level. So therefore we know that polyparamagnetism is an effect associated with the spin of electron. But what about the orbital contribution of electrons? So let's see what is the contribution of the orbital motion of these conduction electrons towards magnetism in metals. So let's begin with Landau levels. First of all, let's consider an electron gas is placed in external magnetic field. So therefore, the time-independent Schrödinger wave equation will be given by h psi equal to E psi, and here the Hamiltonian will only have the kinetic energy term. Therefore, P square divided by 2m times psi will be equal to minus h cut square divided by 2me times the Laplacian operator on psi, and this will be equal to E psi. The solution of this Schrödinger wave equation will be plane waves of e raised to power iota k dot r type with energy equal to h cut square divided by 2me times kx square plus ky square plus kz square. Now let us consider the two cases. In case 1, there is no magnetic field. So therefore, electron states are uniformly spaced in the k space with each point separated by 2 pi by L. But let's see what happens in the presence of magnetic field. For simplicity, let us assume that the magnetic field is along z direction. So therefore, we have charged particles in an external magnetic field, and in the previous video we have seen that in the presence of magnetic field, the momentum operator must be replaced by minus iota h cut del plus E times A vector, where this A vector is the vector potential, and this transformation is known as canonical transformation. So therefore, the Schrödinger wave equation will now become now this Schrödinger wave equation is difficult to solve, and it can be solved by assuming certain symmetry only. And for that, we will introduce the concept of gauge transformation used in electromagnetic theory. You must have studied in your electromagnetic theory that the electric field and magnetic field can be represented as a function of scalar and vector fields. Here phi and A are gauge fields which are not unique. If you transform the scalar potential as phi minus del alpha by del t, and if you transform vector potential as A plus gradient of alpha, then under this transformation, the electromagnetic fields will be unchanged, and the different choices of alpha is known as gauge. As we have told you earlier also, that this equation 3 is difficult to solve, And you must choose a perfect gauge so that the electric and magnetic fields will be invariant under the transformations. One such choice is symmetric gauge, in which you can choose the vector potential to be equal to minus half of r cross b. And if you check, the curl of this vector field will give you the magnetic field B. Here we have taken the magnetic field to be in z direction, so therefore A vector will be equal to, so therefore under symmetric gauge, the vector potential will be equal to half of minus yb along I cap plus xb along j cap. And if you take its individual term, then you will get Landau gauge as minus by along x direction and xb along y direction. So therefore in Landau gauge, there is translational symmetry about x or y axis. It is because y or x value doesn't change along x or y direction. So therefore in this situation alpha will be equal to minus bxy divided by 2, so that the transformation of vector potential will follow this. So therefore we have two choices for the Landau gauge so that the magnetic field will be remain invariant. Here let us choose the second Landau gauge to solve equation 3. So therefore equation 3 will become one divided by 2m times px square plus py minus ebx whole square plus pz square acting on psi will give you E psi. Here you must remember that the magnetic field is invariant under both translational and rotational symmetry in the xy plane. But the vector potential breaks the translational symmetry in x direction. Also it breaks the rotational symmetry. Now since we have manifested the translational invariance in the y and z directions, so therefore the commutator of momentum in y and z direction with the Hamiltonian must be equal to 0, meaning that momentum in y and z direction must commute with the Hamiltonian, so that Py, Pz and Hamiltonian can be simultaneously measured. So therefore we can look for energy eigenstates which are also eigenstate of Py and Pz. And this motivates the ansatz psi of x as e raised to power iota kyy plus kzz times chi of x. This suggests that the energy eigenfunctions are a product of plane waves in y and z directions and some function in x direction. So therefore we can replace operator py and pz with their eigenvalues h cut ky and h cut kz, so that if we put the equation 8 wave function in our Schrödinger wave equation, we will get, and if you substitute the eigenvalues of py and pz, then this will simplify to px squared divided by 2m plus E square b square divided by 2m times x minus h cut ky divided by e b whole square acting on chi will be equal to e minus h cut square kz square divided by 2m times chi. We can simplify this equation 10 if we assume x naught equal to h cut ky divided by eb. If we assume x naught equal to h cut ky divided by eb, which represents the center of a simple harmonic oscillator, and omega c equal to eb divided by m, which represents the cyclotron frequency, then equation 10 will be simplified to a Schrödinger equation for a simple harmonic oscillator, which is displaced by x naught, where this term represents the Hamiltonian for 1D harmonic oscillator with center at x naught. And remember that this is a quantum harmonic oscillator, so that the energy will be equal to h cut omega c L plus half plus h cut square kz square divided by 2 times mass of electron. Here L can take value 0, 1, 2 and so on, and here this chi represents the simple harmonic oscillator wave function. So therefore the wave function of electron gas in magnetic field will become the product of plane wave in y and z direction and the simple harmonic oscillator wave function. This is a unnormalized wave function where this h of L represents the Hermite polynomial and Lb is the magnetic length, and it is defined by under root of x naught divided by ky, which will be equal to h cut divided by Eb. And for 1 Tesla magnetic field, the value of magnetic length will be around 2.5 into 10 raised to power minus 8 meters. If you see here, this wave function depends on three quantum numbers, namely L, Ky, and Kz, while the energy is only dependent on two quantum numbers, L and Kz. So therefore, there must exist some degeneracy arising because we have choices in the values of Ky, which will still give the same energy value. We will calculate the degeneracy in a minute, but before that, let's try to understand what happens to the energy states in the presence and absence of magnetic field. For that, let us restrict electron by forcing Kz value to be 0. So therefore, the energy in this situation will be simply L plus half times h cut omega c, and if you substitute omega c, it will be L plus half h cut Eb divided by mass of electron. This is the situation in the presence of magnetic field. So therefore, in the case when there is magnetic field, the energy level of electrons become equally spaced with the gap between the each level proportional to the magnetic field. But in the second case, when there is no magnetic field, then in that case electrons are free or represent 3D Fermi gas, and the energy levels in this case will have a non-uniform spacing, which follows 1 over n square rule. Also from the dispersion relation, the energies will be quasi-continuous. So therefore the energy spectrum in the two cases looks quite different. It is because in the absence of magnetic field, there exist discrete electronic states, but in the presence of magnetic field, k vectors condense on tube parallel to the magnetic field. So therefore, in the absence of magnetic field, the electron states are uniformly spaced in the k space, but the application of magnetic fields result in only certain allowed energies. These energy levels are known as Landau levels. In 3D, these circles will be converted into concentric cylinders or tubes. This happens because in 2D, the energy is given by h ket square, k square divided by 2m, which will be equal to L plus half times h ket omega c, and the value of k square can be equal to kx square plus kz square, and which will be equal to a constant from our equation. So therefore this represents equation of circle for each Landau level. If you bound these Landau tubes with the Fermi energy, then you will see something like this, where concentric cylinders are limited by a sphere of radius kf, or the Fermi radius. Here the Fermi surface cuts different Landau tubes for different values of kz. So let's try to understand the physical interpretations. The first one is that the magnetic field confines the motion of electron in plane perpendicular to the magnetic field, creating quantized orbitals. And along the field direction, the electron is free, hence there is continuous values of kz, so that the allowed energy states for each Landau level forms a tube of constant energy labeled by value L and extending along kz. Now let us try to calculate the degeneracy associated with each Landau level. Consider the situation in 2D when kz is 0 and the wave function depends on two quantum numbers L and ky, while the energy is independent of ky. So therefore for a particular energy state, we have a large number of choices of wave functions, and this corresponds to the degeneracy. So therefore the Landau levels are not unique, and there exists a huge degeneracy with many states having the same energy. If you see in the presence of magnetic field, k vector forms in the form of circles, each labeled by integer value L, so that we can calculate the area between any two circles as pi k L plus 1 square minus k L square. The degeneracy in this case will be given by area of annular region between k L plus 1 and k L divided by the separation between each electronic state in k space whole square. And you must remember that there exist two electronic states, so this whole thing will be multiplied by 2. So the degeneracy will become 2 times pi k L plus 1 square minus k L square divided by 2 pi by L whole square, where the numerator is the area between two Landau levels in k space and the denominator is the area occupied by one electron state in kx and ky plane. So therefore the degeneracy will be equal to 2 pi L square divided by 2 pi whole square times k L plus 1 square minus k L square. And if you see here in the energy expression, k square will be equal to L plus half times h cut omega c times 2 times mass of electron divided by h cut square. So therefore the degeneracy will be given by and the simplification will give L square me omega c divided by pi h cut, which will be equal to L square eb divided by pi times h cut. So therefore the degeneracy of Landau levels is proportional to the magnetic field value. Let's put some typical values of area equal to 1 centimeter square, magnetic field of 0.1 Tesla, and the value of h cut equal to 1.38 into 10 raised to the power minus 34 joule second. Then you will see The degeneracy is of the order of 10 raised to power 10, which is a very large value. So therefore, there are around 10 raised to power 10 degenerate states per Landau level of electrons in a region of area 1 centimeter square in the magnetic field of zero point 0.1 Tesla. This large degeneracy ultimately leads to an array of dramatic and surprising physics, such as quantum Hall effect, De Haas 1 alpha effect, and Landau's diamagnetism. This is it for today, and we will talk about Landau diamagnetism in the next video. Thank you so much for watching this video.